Okay, folks, here we go. So, we finished up our integration, our multiple integration or iterated integrations to essentially find areas and volumes, or, finding the mass by integrating a density function or finding, average function values like average temperature over a solid 3D region. And we're going to be interested in vector fields and integrating over curves through vector fields for, a good portion of chapter 17. So let's define a vector field in 2 dimensions. Now, you've already essentially seen a vector field. When you look at the gradient of a function that gives a surface, when you look at its gradient, the gradient is really just a vector field. The gradient is a vector field in 2 dimensions, and it indicates, at any point on the surface, its gradient would indicate, the gradient vector would indicate the direction of steepest ascent at that point, and minus the gradient would indicate the steepest descent at that point. But, if you consider the gradient of a surface over its domain, the gradient is a vector field. So if you take f and g to be found on a region, so we'll do vector fields in 2 dimensions first. So definition, if f and g are defined on a region R in 2-dimensional space R2, a vector field in R2 is a function f that assigns to each point in R a vector with components f of xy and g of xy. You can look at how the notation for a vector field is capital F of xy. Remember, capital F is just, bold-faced F is just notation for a vector, right? Whenever you use bold-faced or bold script, if you were writing this by hand, you would write capital F with a vector arrow on top. And you can either write it in component form with angle brackets, or you can write it in the ij notation, where I and j are the unit vectors in the positive x and positive y direction, respectively. The vector field f with component functions fg is continuous or differentiable whenever the component functions f and g are continuous or differentiable on the region R, respectively. So example 1, if I look at the vector field capital F of xy and that has components x comma 2x, we're going to sketch some representative vectors of the vector field F. So I'll probably just do like 2 or 3 of these, just for emphasis. Like, if I do, you can do like f of 1, 0, and that would be 1 comma 2. I could do f of 2, 2, and that would be 2 comma 4. You just notice that the second component is doubling the first, and notice that none of these vectors in the vector field depend on the y-coordinate, since the components are x and 2x. I can do another one, f of 2 comma 3 is also 2, 4. Oops. Maybe I'll do one more. How about like f of, do f of 3, f of 3, 1, which would just be 3 comma 6. Now I'm going to plot these 4 vectors. Now you want to plot them, you don't plot these all in standard position. So for instance, if I look at this first one, if I'm looking at, and you know what, I'm forgetting all my vector arrows on the tops of these. So what I'm going to do is, at the point 1 comma 0, I'm going to draw a vector that goes 1 unit to the right and up 2 units. Oops. So let's see. Go to the point 1, 0, which is right here. Oops. It's hard for me to draw with my little pen. And then what I'm going to do is I'm going to go right 1 and up 2 to get to the head of the vector. So there is the vector 1, 2 at the point with the head, or sorry, the tail of the vector at 1, 0. Okay, and then remember the components of the vector 1, comma 2, just say from that tail you go 1 unit to the right and 2 units up. Now, the vector, if I look at capital F of 2, comma 2, that gives me the vector 2, 4. And again, 2, comma 2 is going to be the tail of the vector, and I'm going to go 2 units right and 4 units up. 2, 3, 4. So there would be the head of the vector. Okay, so there's another vector in my vector field. Just plotted this one right here. And then f of 2, 3 is 2, comma 4. And don't think I'll be able to actually plot this one in here just because, so let me get rid of these two. So now if I want to plot this one at the point 2, comma 3, that's going to be where the tail of the vector is, and I would go 2 units right and 4 units up. That's where the head of the vector is going to be. And if I want to do f of 3, 1, so at the point 3, comma 1, that's where the tail is going to be. And I'm supposed to go 3 units to the right and up 1, 2, 3, 4, 5, 6 units. There would be another vector. Okay, so whatever the points are. So if I'm doing, again, if I look at this bottom one, f, capital F of at the point 3, comma 1, I would draw a vector with its tail at 3, 1, and the components are 3 and 6, so I'd go 3 units to the right and up 6 units to find the head of the vector. So I guess the inputs x and y determine the tail of the vector, and the components, or the output of the function, determine those are basically just the directions to get to the head of the vector. Okay, so again, the inputs are where the tail is, and the output, the components, tell you how to get to the head of the vector. Okay. So, you can use Mathematica to plot these as well. You're just going to use the command vector plot, type in the coordinates, and you can get a range of values if you want. You could do x is going from, say, -3. Sorry there, I got distracted. Someone stopped by the office. But yeah, I can do a vector plot command. Now this would be a two-dimensional vector plot, and then in curly brackets you'll just write the components like x, comma 2x, and then you can give a range of values. Actually, I'll go minus, let's go minus 10 to 10, and y is going to go minus 10 to 10, and there would be your vector plot. One thing I want you to notice is that at any point where the x-coordinate is the same, you're really just getting the same vector just being translated, right? You're just the same vector. Just for example, if you look vertically at this collection of vectors in the vector field, notice the vectors themselves only depend on x. So the y-coordinate doesn't really matter, so along any vertical line you're going to get copies of the same vectors. One thing that I might want to notice is that I don't necessarily know if these vectors are up to scale. You'll notice as you move to the right or to the left, the vectors are increasing in magnitude, so as the x-coordinate increases, the magnitude of the vectors are growing. But they're not necessarily, I don't know if they're really up to scale or not. Now you can change the size of the vectors. Just give me, I gotta go look at the command for how to change change the vectors, or how do you get more vectors to appear in your vector plot, because these are not all the vectors. This gives you a general idea of what the vector field looks like. Okay, so it turns out I just did the same thing. You can add so after you put the components of your vector field function in there, and you specify your range of values for x and y, you can use a vector scale command, and then you'll just use like a dash and then right arrow, and then you can do like 0.1 or 0.04 if I want them to be smaller. And do 0.1, 0.2. But after a while it starts getting ridiculous. The vectors fall on top of each other. So I like a vector scale 0.1 here to display this vector field nicely. Okay. Now, there are a special kind of vector field in R2, and then there's going to be an analog for this in 3 dimensions, or R3. So if you let R just be the vector field with components x and y, a vector field of the form f equals f of x, y, comma r, where f is a scalar valued function. So this could be like, basically this would just be like a function that gives a surface, right? Your outputs are real numbers. Then you multiply by the vector valued function r. I guess it's not really a vector valued function, it's a vector, r is a vector field. Remember, a vector valued function has a single independent variable t, so that's what a vector field actually has 2 independent variables, x and y. But you can use any scalar valued function f. This is called a radial vector field. And what happens is essentially it's called a radial vector field because all the vectors are going outward from the origin. And of specific interest are radial vector fields, where you take your vector field r with components x and y and you divide by the magnitude of r raised to any power p, where p is a real number. So at every point except the origin, the vectors of this field are directed outward from the origin, and the magnitude of f ends up being 1 over the magnitude of r to the p minus 1. You can go ahead and work that out on your own. So now example 2, I could look at the vector field capital F of x, y, and this ends up being this is a radial vector field where lowercase f of x, y is just the constant function 1. And the other thing here that's interesting is, if r was equal to x, y, then capital F in this case, which is just the vector field with components x, y, this is just r divided by the magnitude of r to the 0 power, if you like, which just gives you back r. So really it's a radial vector field where p is equal to 0. And again, we could draw a bunch of representative vectors if we wanted to. I could draw a couple in there, but I'll just go ahead and use Mathematica just to see what this looks like. Actually, I don't even think I'm going to specify x and y. Let me see what happens if I just do that. Okay, so it does want you to actually specify a range of values for x, a range of values for y. And there you go, there's a radial vector field. You can see that when you look at every vector, they're extending outward away from the origin. And hence why it's called a radial vector field. Okay. One other thing I forgot to mention is, and you can read this in the book if you want to. There's lots of applications of vector fields. Like one is you could, if you think about a river and you think about the current, the river is going to bend and it's going to turn, and the flow is going to be stronger in some parts. So you can think of vectors with high magnitudes. And also those vectors are going to go in the direction of the flow of the current, and they're going to be stronger. They're going to have larger magnitudes. They're going to be longer vectors where the current is going faster. And then out on the edges of like when you turn a river, there's going to be the slow part of the turn. Those are going to be the flow there is going to be smaller, so at those points on the river where the flow is slow, you're going to have vectors that indicate the direction of the flow, but if the flow is slow, they're going to be vectors with smaller magnitudes. You can think about electromagnetic fields. You can think about wind patterns. You can think about dropping chemicals into a body of water. The chemicals are going to flow in some certain direction. So vector fields have lots of applications. Okay, and we'll look at some specific ones later, especially when we start thinking about curves traveling through vector fields and thinking about think about how the vector field is acting on a curve. So those are things that we're going to do later. There are vector fields in 3 dimensions, and we could go ahead again and we could draw some representative vectors if we wanted to, but this time you're going to use, if you wanted to use Mathematica for this, you can do a vector plot 3D, specify the components, and this time you'd have to give a range of values for all 3 of the variables. And what did I do wrong here? Give me a second to figure this out. Okay, so it turns out that I had to use the math palette and use the special symbol for E. I think you could also use like EXP too. I think I could do EXP of negative Z. There we go. Okay, so here's a vector plot. X and Y go from -10 to 10. Z is specified to be greater than or equal to 0 in this example. So here's your vector plot. I believe you've got it doesn't really matter which one's the x and which one's the y-axis. My vector scale, I just used 0.1. As you start using like a vector scale of 0.5 or larger, the vectors become so large they're on top of each other and you can't even really see anything anymore. Couple cool things about this vector field: if I move my image and look at this directly from the top, you kind of see that this is radial in terms of x and y. So this is looking at the projection on the xy plane. Right, so all the vectors are moving out from the origin in the xy plane. And then one thing you might notice is if I flip this back up again, as I go from 0 to 10, e to the minus z is going to be getting smaller as z goes from 0 to 10. So you might notice that if I look at z equals 10 up here, Right, this is z equals 0. You'll notice that the vectors don't really have much of a vertical component. When z is equal to 10, there's much more of a vertical component when z is equal to 0. Okay. Anyways, there's a cool example of a three-dimensional vector plot. Okay. Now, one thing this is going to become a lot more useful later on is talking about gradient fields and potential functions. So one thing I want you to think of for now when you think of this is when you're given a surface and you find its gradient, okay, well, the cool thing is that given a surface and its gradient, the function that gives you the surface is actually what's called a potential function, and then it has its own gradient field. So I remember I mentioned earlier that the gradient of a surface is really just a vector field, and the original function lowercase f would be what's called the potential function. Okay, so example 4, this is going to be nothing really new. If I take this potential function phi, which is cosine of x minus y plus sine of x, this would graph some surface. I can find its gradient field, and that's not going to be too difficult. So if I look at if I take capital F to be the gradient of phi, the components are going to be the partial derivative of phi with respect to x and the partial derivative of phi with respect to y. And let's see what our components are. The derivative with respect to x, well, the derivative of cosine of x minus y would be negative sine. Inside stays the same. And the derivative of the inside with respect to x is 1 plus, and then the derivative of sine of x is cosine of x. And hold on, I should rewrite this so I actually have some room. And the second component is the derivative with respect to y. The derivative of cosine is minus sine, but the derivative of the inside is minus 1, so you get sine of x minus y plus 0, because the derivative of cosine x, or the derivative of sine x is 0 with respect to y. Okay, so there's your gradient field, and notice it's a two-dimensional gradient field of a three-dimensional surface, which is kind of cool. Now I'm going to go ahead and just do a vector plot with this, see what it looks like. Is minus sine of x plus y plus cosine of x, comma, and then it was sine of x minus y. I can do x from negative 10 to 10, y from negative 10 to 10, and that is just a bonkers looking vector plot. Now, one other thing I can do is I can do a plot 3D, and I can plot the surface, the original surface. So I'll plot the function phi cosine x minus y plus sine x. And I'll go ahead and do this again from x equals negative 10 to 10. And y goes from negative 10 to 10. There's an image of the surface, a view on the top. And if you think about this in terms of surfaces and gradients too, all the vectors in the vector field are giving you the direction of steepest ascent at any of the points along this surface. Now, another thing I could do is I could do the contour plot. So there's my contour plot of the surface. I think that anything in blue, those are the higher points on the surface, and anything in white, those are the dips or the lower points on the surface. I believe that's correct. You can compare all three of these. Okay, so what I was going to do is, again, we found the gradient field of that potential function, which is really just the gradient of the surface. All these vectors are giving you the direction of steepest ascent at any point along the surface. Here's the surface right here. And then just for fun, I also graphed the contour plot, so this would just be a collection of all the level curves. So there's a strong connection between all three of these. And I was trying to plot them together so you could get a look at them, but you'd probably have to, I'd probably have to do like a vector plot 3D and let the z component always be 0. So I could do vector plot 3D, add a z component of 0, go from z negative 10, well, I'll just go from 0 to 10. Unfortunately, though, I get all those copies. I didn't really want that necessarily. So I don't know if I can really get this to work like I wanted it to. So I would ignore that part. I would just think of the original vector plot. Get rid of the 0 component. There's my original vector plot. There's the surface. If I look at it directly on the top, and again, I wish I could get these together. I could probably get them on the same image though here. You could compare the two, and all these, again, all the vectors up top are giving you the directions of steepest ascent and the directions of steepest descent on the surface below. And then again, there's just a contour plot. Okay, so the another thing I wanted to maybe point out, and I was getting at this for example 5, is all of these vectors in the vector plot of the gradient. Okay, so again, that's the vector plot of the gradient of the surface. All of those vectors in the vector plot are going to be orthogonal to all these level curves in the contour plot. So remember, the gradient is always orthogonal to the level curves. So we're going to revisit that here. So if I consider a temperature function, capital T equals 200 minus x squared minus y squared over the region, which is going to be everything inside and on the boundary of a disk of radius 5, we're going to find the gradient field of T and verify that the gradient field is orthogonal to the equipotential curves, which are just level curves. Okay. Alright, so I want to find the gradient field of T. So the gradient field of capital T is just, okay, it's the partial derivatives, tx, ty, which is pretty easy in this case, minus 2x minus 2y. Okay, and then I want to show that's orthogonal to the level curves. So what do? You take, what's an arbitrary level curve look like? You set capital T equal to a constant, and I can subtract the constant from both sides, 200 minus x squared minus y squared minus c equals 0. And then you can use implicit differentiation. If I call this, oh, maybe I don't want to call it capital F, but just call the function on the left g if you like. Then if you look at dx dt, so this would be the slope of a tangent line at any arbitrary point on a level curve. It was minus gx over gy. And this is going to be, actually sorry, that's the other way around. It's minus gy over gx. So you end up getting negative minus 2y over minus 2x. So you get minus y over x. Okay. So that tells you basically the slope of the tangent line along any level curve. And now you can find a vector that's tangent. So remember, the numerator this is thought of as the change in the x direction, and that denominator is the change in the y direction. Okay, so if I was on the curve and I wanted to find a tangent vector, minus y is the change in x, and x is the change in y. And if the gradient is going to be orthogonal to the level curve, so I take a vector that's take a vector that's tangent to the level curve, which would be minus y comma x, and dot it with the gradient, which is minus 2x comma minus 2y, you're going to get 2xy if you multiply the first components, and then minus 2xy, and you're going to get 0. Okay. So in my dot product here, the first vector is that's a vector that's tangent to the level curve, and the second vector is just the gradient. Okay, that's the gradient field of T, and they're orthogonal if their dot product is 0, which it is. Okay, so that's all I've got for everyone. For this section, I'll probably just do online homework. I don't think I'll do any written homework. So take a look at the online homework, watch this video, and I'll see everybody in class on Thursday. Thanks for watching. Take it easy.